Hi, in this video we're going to be talking about concurrency. Okay, so before we go into the actual OS concurrency concepts, let's just have a quick overview of how architectures can be designed to achieve concurrency. Okay, so these are some of the common terminologies you may come across in textbooks, okay, and online material on how systems can be designed, okay, to handle concurrency at a hardware level. Okay, so the first one is of course what we are used to, single instruction and a single data stream, uh, very much similar to our single threaded environment. Okay, at the hardware level also, everything happens sequentially. Okay, so you can think of our how we were running our labs, okay, before the OS came in. Okay, so we have a single processor, and every time I fetch an instruction and there is some data associated with it, and we process it, and then we get some result. Okay, the next thing that we can go towards is what we call MIST, multiple instruction and single data. Okay, so I fetch a single data, okay, but that same data, I can process it uh, with different units concurrently. Okay, so different instructions are coming out, okay, are being fetched from the instruction pool, and I'm processing the same data with multiple instructions at the same time. Okay, so that is another architecture. The other third one is what we call the SIMD, single instruction and multiple data. Okay, where you can say that with a single instruction coming out, okay, the same instruction is going to work on multiple sets of data at the same time. Okay, so again you can see there are multiple processing units, and of course the most complex type is MIMD, multiple instruction, multiple data streams. Okay, so I have a lot or multiple instructions coming out, and at the same time multiple data coming out, and a lot of things are happening concurrently within the processor at the hardware level. Okay, so this is a quick overview, okay, on these four different types of architectures. We call it Flynn's taxonomy, basically because this CS professor Flynn is the one who initially came out with this idea of how concurrency can be achieved, okay, with the design of hardware in terms of processing units, as well as tapping onto multiple streams of data and instructions. Okay, so this is just giving you an overview. Of course, what we have been doing all the while is SISD, sequential code. Concurrency at the hardware level. Okay, so in this case, hardware level is talking about hardware subsystems that can uh, behave or operate concurrently regardless of the software. Okay, so for example, if I have already configured my PWM block, okay, to operate at a particular rate duty cycle, it can go on indefinitely without any software intervention. Similarly, if I have a timer interrupt, it can also go on without any other software intervention, or a data packet or a buffer that is continuously read and sent out through a serial interface that can also go on concurrently. Okay, so I can achieve concurrency at the hardware level, but in terms of software execution is still sequential. Okay, so that is what we have been dealing with all the while, the SISD sort of architecture. And uh, for us currently in this module, we're also looking at operating systems on single processors. Okay, and that is a bit a good starting point, okay, for all of us, because in terms of looking at it from the memory and data management, it is fairly easy, and the scheduling policy is also consistent. Okay, so a single OS, okay, and on a single processor you have a very consistent way of looking at how the multiple tasks or threads are going to be operating, how we deal with the memory and so on. Okay, so it's a good starting point for all of us to get or to transition from a single threaded environment to a multi-threaded environment. Okay, so when we go from single threaded to multi-threaded, okay, things are not so straightforward. Okay, are not so straightforward because a lot of things can happen. Okay, and if you look at the picture here, what we are trying to show you is a very common issue where in a single threaded environment, only one thread is running at a time. So if I'm accessing some memory location, I can complete the memory location, complete that memory access, and then the next code or the next thread can run, okay, and then the memory access can be done again. But in a multi-threaded environment, two threads, okay, two threads can be trying to access a shared memory resource. Okay, and when that happens, okay, it can lead to a lot of challenging issues. Okay, and one of these issues is what we call a race condition, where a set of processes or tasks try to access a shared resource, okay, and do some computation on it. Okay, and in this situation, the result, okay, of the computation depends on exactly the sequence and how the different tasks have been interleaving. Okay, so what you will observe is sometimes it may seem that it's correct, and sometimes the answer may not be correct. Okay, and that is basically a race condition because it depends on how the tasks were actually switching around. Okay, which task got to run first, which task got preempted, and so on. Okay, so that is a very tricky situation because you may not see the error or the data being wrongly updated all the time. Okay, sometimes it seems correct, sometimes it seems wrong. Okay, so that is what we're going to be looking at now. Okay, and this is important because it undermines the correctness of a multi-threaded system. So we must do our part to ensure that race conditions are eliminated, so that even if a task is running and it gets switched out, okay, that data that it was working on, it still is sort of locked by the current task and no other task is able to access it. Okay, so in terms of shared resource, okay, what do we mean? We can generally we can say it's a shared variable. Okay, maybe a global variable. Okay, or even objects such as files or even devices. Okay, when we say devices, could be a device connected to our port, a serial interface, and so on. Okay, so anything that is shared between multiple tasks is a shared resource. Okay, so let's look at this example of how a race condition can occur. So in this code, we have a function called increment k, and the objective of this function is to increment a variable called k by 1. Okay, and we have two threads, function A and function B, which are both created here. Okay, so of course, not the whole code is given here, but in basically OS thread new, these two are actually in the main. Okay, so due to space constraint, I didn't want to squeeze too many things here. But basically, once I call OS thread new function A and function B, we know from what we have already done in our labs that we have two sort of threads, one for function A and one for function B. And as we saw, all our tasks or threads are written as infinite loops. Okay, and in both these loops, I call the same function increment k, and then I do other things. Okay, uh, of course, there could be other tasks in the system, and these other things here could also put one of these tasks into a ready mode or a block mode. Okay, depending on a lot of other things. Okay, so we are not going into all the details, but the basic idea is function A and function B both are accessing the same function called increment k, which is accessing a shared variable called k. Okay, at any point of time I can switch out from function A to function B or from function B to function A. Okay, so we do not know when this can happen. Okay, anytime this can happen. So that is the sort of baseline from which we are going to analyze this code. Okay, so the important thing you must understand is this operation k equals k plus 1, okay, is in C is a single line statement, but when you compile it to assembly language code, okay, we must understand that this is not a single atomic operation. Okay, it is not. Okay, why? Because a RISC system, okay, like our ARM processor, cannot do a direct operation on a variable in memory. Okay, so I need to break up this operation into 3 steps. The first step is to first load from memory. Okay, that means load the data from the memory to our internal register, then do the operation, in our case is the add operation, and then finally I'll be able to store back the register value to the memory. So this single line in C is actually translated into 3 lines in the assembly. Okay, and that is where the challenge comes in, because when we talk about one task getting preempted by another task, okay, that preemption can happen anytime. Okay, and we have to look at it from the assembly language code. Okay, because each of these lines is actually an instruction that your processor will execute, and when a context switch happens, it can happen anytime. Okay, so that is where we need to be careful. So in terms of um, the execution of the single line in C, we can now relate it to three sort of instructions at the assembly level. Okay, the first one is to load. Okay, then we do the operation, which is increment, and finally we write back. So these are the three operations at the assembly language level. Now let's think of this as analysis on what will happen if both the tasks are running concurrently. Okay, and if my initial value is k 0, I would expect that after both the tasks complete, the final value should be 2. Okay, so that is what we expect, because each task is going to increment k by 1. Correct? So if I start with 0, after both the tasks complete, k should be 2. Now let's look at what would happen if I follow the sequence that I think would happen, where one task runs and then the other task runs. So either task A first and task B, or task B and then task A. Okay, or function A, function B, function B, function A. Okay, so in this situation, okay, what we expect is if task A runs first or task 1 runs first, I will load the value, increment it, and write it back. Okay, so at this point of time, k is originally 0. When I complete this first task, it will become 1. And then my second task runs. So task 2 runs, I will load the value of 1, increment, and write back. So from 1, it will become 2. Okay, so this is the expected result. Okay, but since in a multitasking environment, anything can happen anytime, correct? So anytime a task can be running and then switch to a ready mode or switch to a block mode. Okay, so in that situation, what can potentially happen? Okay, so initially my value is 0, correct? And let's assume task 1 runs first. So it loads the value of 0 inside here, and then it increments it. So from 0 it becomes 1. Okay, but it has not completed the write back. And before I can complete the write back, I do a context switch from task 1 to task 2. So task 2 is also going to do a load. So it loads a value of 0 inside here, and it increments. So it becomes 1. And then what happens? You do another context switch back to task 1. So what does task 1 do? It has already done the increment. So it has to complete the operation by doing the write back. Okay, so the write back will then come here, and I'll write a value of 1 inside here. And finally, I will do another context switch back to task 2, and the task 2 will also do a write back of a value 1 inside here. So you can see that because I got preempted, okay, at the stage where I did the increment but could not complete the write back. Okay, so what happened was the subsequent task that did a load was still loading the previous value of k and not the updated value of k. Okay, so even after two tasks running in parallel with my initial value of 0 for k, I still end up with the final value of only 1 instead of 2. Okay, so again, this is a tricky thing because like I mentioned, this may not happen all the time, correct? Because this depends on the dynamics of how the two tasks are going to switch around. Okay, so sometimes you may see the value is correct, sometimes you see the value is wrong. Okay, so that is where the challenge comes in. Results are incorrect only sometimes. Okay, so this is again an important point, and it is very critical that we handle this, correct? So how do we eliminate race conditions? Okay, so the way to eliminate race condition is to first identify these potential points of uh, hazard. Okay, and how do we do it? Basically, as long as we know that there are shared resources between multiple tasks, accessing these shared resources, so the code that accesses this shared resource is basically what we call a critical region or critical section of the code. Okay, so any region of the code that is going to access this shared resource, we call it a critical region or critical section. And what we need to do is we need to protect this critical section. So how do we do it? We use within the OS, we have this OS construct called Mutex or mutual exclusion. So what does a mutex do? It basically controls access to the shared resource by providing exclusive access. That's why we call it mutual exclusion. So when one task is having it, okay, uh, any other task that wants to have access to a shared resource must be in a block state waiting for it. Okay, so it ensures that only one thread of execution can happen at any point of time. Okay, now how do we use this in our code? So for example, thread A and thread B. Okay, now, and both of them are accessing a shared resource, which is K. So K, which is actually through our increment K function, this is our shared resource or critical section of the code. So first step, we must understand that this is a shared resource, and what we want to do is we want to protect this shared resource by using a mutex. So we must have a rule. Okay, the rule is basically that before I access this shared resource, I must do a mutex lock. Okay, and after I am done accessing the shared resource, I can do a mutex release. Okay, so these are the two important things I must follow. Okay, before I access the shared resource, I must lock it. After I have accessed the shared resource, I must release it. Okay, so now let's assume that we have both the threads, thread A and thread B, going to run, and thread A runs first. Okay, and when thread A runs, it does a mutex lock. Okay, so I have completed my requirement to make sure that before I call the increment K function, I do a mutex lock. And what I'm showing you is after I do the mutex lock, something happens and I'm doing a context switch. Okay, so maybe thread B is higher priority, or for some reason thread B is now chosen to run. Okay, so when thread B is now chosen to run, okay, thread A goes to ready state. Okay, now when thread B runs, thread B is also going to call the increment K function. Okay, and the rule is that before I can call increment K, which is a shared resource, I must do a mutex lock. So the thread B tries to do a mutex lock. So at this point of time, what happens? At this point of time, the OS knows that the mutex has already been locked, okay, by thread A. Okay, that means thread A is in the middle of accessing this shared resource. So when thread B tries to do a mutex lock, it is unable to do it. Okay, so it will fail the mutex lock. So because of that, it will go into a block state. Okay, and what will happen is since it goes into a block state, again the scheduler will be invoked, and if there are no other tasks in the system, then of course I'll do a context switch back to thread A. Okay, and thread A will then go from ready back to run state, and then it will be able to access the critical section of the code, which is increment K, and when it is done, it will eventually release. Okay, but when it releases the resource, then what happens? Okay, when it releases the resource, there will be a the OS will come in to unblock. So at this point of time, it will unblock the task B and switch it to ready mode. Okay, so at this point of time, when the mutex is released, task B or thread B will transition from block state to ready state. Okay, and subsequently, again, whether it goes to run or not, it depends on the scheduler and the policy. Okay, so in this case, if thread B is same priority than thread A, then maybe it has to wait for its turn. Okay, if thread B is higher priority than thread A, then once it goes to ready, it will automatically transition to run. Okay, so the important thing is this part here. Okay, why is this important? Because this tells us that when thread B, okay, so I think this is until here. Okay, when thread B is trying to access the shared resource, it tries to do a mutex lock, but because thread A had already locked the mutex, okay, thread A already locked the mutex, that means it is in the middle of accessing the shared resource. So thread B, since it's unable to lock the mutex, is unable to carry on to access the shared resource, so it's going to go to a block state, which will then again initiate the scheduler to come in and do another context switch to the next task that is able to run. Okay, so that is how we are able to use this idea of a mutex, okay, to control access to a shared resource. Okay, so you can see that in this situation, whichever thread gets the mutex first will be able to carry on and complete the access to the shared resource, and then after it is released, then the next task that is waiting for the mutex will be able to access the shared resource. So it's always going to be one task fully completing the access, then the next task. Okay, which is basically what we want to achieve, correct? We want to ensure that when I am accessing a shared resource, even if I get preempted, nobody else gets access to the shared resource. Okay, so that is the important thing that we must understand here. So the in RTX OS, which we are going to be using, or which we are using right now, okay, the mutex functions are as such. So firstly, I need to create a mutex ID globally. Subsequently, I can create a new mutex, okay, using this OS mutex new kernel call. And to acquire and release are these two functions here. Okay, so these are the default ways in which we use it. Of course, in the labs and tutorials, we are going to be exploring some options, okay, so that we better understand the different ways in which this mutex can be used in our code. Now, besides mutex, there is also another very common OS construct called semaphore. Okay, so the whole idea of semaphore is instead of a single resource, we can say a group of resources, and we manage this group of resources using what we call a token system. Okay, so if I want to access a resource, I must get a token first, and if I can get the token, I can use the resource. And once I'm finished with the resource, I return the token. Okay, in some cases you can use semaphores in a similar fashion to mutex, but in some other cases you can use semaphores in a more complicated way as well. Okay, so again, when we say a number of resources, okay, think of it as maybe our timers. Okay, so we may have three timers: timer 0, timer 1, and timer 2 in our system. Okay, and at the same time I can have maybe up to 10 tasks. Okay, and all these 10 tasks all want to use this timer. Okay, so instead of uh, allocating or fixing a particular timer to a particular task, you can design architecture such that whenever a task wants a timer resource, it tries to acquire a semaphore, and if the semaphore is acquired, then you allow it to make use of one of the available timers. Okay, so at any point of time, there are three timers, and multiple tasks are waiting to use these three timers. Okay, and semaphores could be used as a mechanism to control the access to this shared resource. Okay, so that is the idea of how a semaphore can be used to manage shared resources among multiple tasks. Okay, and for the primitives, okay, or the OS construct that we will normally use in terms of the material, teaching material, we call it the P and V. P is basically semaphore take. Okay, so we call it the semaphore take or semaphore acquire. And V is to semaphore give or release. Okay, so again, different maybe literature, different textbooks may have different terminologies, but it's the same idea. Sem take is basically to acquire the semaphore. Sem give is basically to release the semaphore. Okay, and since it is a token counting system, what happens is whichever count value you start with, whenever you want to take, you will decrement it. Okay, so of course you must first have some resource, and then you take, and then you decrement. If you try to take and it is empty, that means there are no resources available, what will happen is you will go into a block state. Okay, so you'll go to a block state. That means you wanted to acquire a resource but you are unable to get it, so you go to a block state. Again, similar idea to mutex, correct? In mutex also, you try to acquire the mutex and you are unable to do it, you go to a block state. Okay, and once you are done with the shared resource, you can release the semaphore. Okay, and when you release or you sem give, then you increment the token count. Okay, so you increment it. Okay, and if somebody else was already waiting for it, it was already blocked, then what happens is instead of incrementing it, you automatically allocate it to the task that was waiting in the queue for the semaphore. Okay, so let's look at this example here. So my initial value of semaphore is 3. Okay, 3 resources, and if I first take it, then what happened? Since I got an initial token count of 3, it will become 2, and I take it again. Okay, so again becomes 1, and once I'm done, I may release it. Okay, so the first resource I've done, so I'm releasing it, so it becomes 2 again. From 1 it goes back to 2, and then another task comes in, it acquires the resource, so it becomes 1. Another task comes in, it acquires the resource, becomes 0. So at this point of time, what happens? Your semaphore count is 0 means, okay, if any other task comes along and tries to get a semaphore, it is unable to do it because the count is 0. That means there are no more resources available. Okay, so when another process comes along and it tries to take it, it is unable to do it, so it gets blocked. And when it gets blocked, it is joining a queue. Okay, so X is in the queue waiting for a semaphore to be available. Okay, now when another process comes along, so process Y comes along, and the process Y also tries to acquire a semaphore and is unable to do it, so again it is blocked and is joining the queue. Okay, so X came first and tried to get a semaphore, it couldn't get, so it's joined the queue. Y came next, it tried to get a semaphore, couldn't get it, and it's going to join the queue again. Okay, now when at this point of time, what do you see? One of the tasks is releasing a semaphore. Okay, and rightfully, when you release a semaphore, the count should increase, but in this case, the count does not increase. Why? Because there was already a process that was blocked, okay, waiting for a semaphore. So automatically, the resource that was released gets allocated to the process that was waiting in the queue. Okay, so the process X that was waiting gets the resource, and so it becomes unblocked. Okay, so you remove it from the queue. Okay, similarly, the next person who releases another resource also does not affect the count because there was also another task Y, that was waiting in the queue. Okay, so when another resource is released, the count does not increment, it automatically gets allocated to the task that is currently in the queue. So the task that is in the queue, task Y, gets the semaphore and becomes unblocked. Okay, so it is no longer in the queue, and subsequently, whenever I release, since there's nobody else in the queue, my count can then go up. Okay, so that is how we are able to use semaphores as a tool to manage multiple resources across many tasks. Okay, so in our RTX, we have these constructs to use. So as you can see over here, what I've done is in this sample code, you first create a semaphore ID, okay, similar to Mutex ID. These are all global, and subsequently I create a new semaphore. So for a new semaphore creation, we have two counts, two numbers to put in. One is the max count and initial count. Generally, max count and initial count are set to be the same, okay, because when you start the system, all your resources are available, okay, and subsequently, whenever a thread acquires a resource, then the count changes. Okay, so generally for OS semaphore new, the max count and initial count are the same. Okay, now in this sample code, I've given max count and initial count both as 1. Okay, both as value 1. Okay, and if you look at this sample code, what I've done is I've used semaphores in a similar way to using Mutex. Okay, basically before I access this shared resource, in this case, which is the LED, I acquire the semaphore. Subsequently, once I'm done, I release. Here also I acquire, then I release. Okay, in the lab, you'll also see the same thing I can do with Mutex. So here also I can do Mutex acquire and then Mutex release. Okay, and same thing here, Mutex acquire, okay, and then Mutex release. Okay, so if I declare or initialize my semaphore with a initial count as and max count as 1, then basically it is just 1 going to 0 or 0 going to 1, correct? Okay, and that is basically what we call a binary semaphore. And a binary semaphore is actually very similar to the same way that Mutex behaves, okay, because you only have a single resource. Okay, but there is one other thing, which is priority inheritance. Okay, what is priority inheritance, which we will sort of discuss this more in one of the tutorials. Okay, but for now, we can just take it that a semaphore with a count of 1, okay, is in a sense similar to a mutex. Okay. Now, of course, important thing is, like I said, generally we use mutex, okay, for critical sections, okay, critical region or critical section of the code. Semaphores are generally used for resource management. Okay. Again, this is just a guideline only. As you saw just now, it is still possible to use semaphores as a tool for critical section protection. Okay. And there's nothing wrong in that. But of course, this is the general guideline of using semaphores and mutex. Okay. And of course, one of the key things, which is the priority inheritance, we will be discussing more of that in the future tutorial. Okay. And of course, another important thing is Semaphore does not keep track of the order of access of shared resources. Okay, so it treats all resources as identical. So in the example just now, if I say I have 3 timers, timer 0, timer 1, and timer 2, and I create a semaphore with the initial count of 3, whenever I try to acquire a semaphore, it does not keep track of which timer was already allocated. As far as it's concerned, all 3 timers are considered equal resources. Okay, so it is up to you as a programmer to decide whether that is the concept or the idea that you have. Okay, if the 3 timers are going to be used in very different contexts and you do not want them to be treated as equal, then you should not have like a semaphore with a count of 3. Okay, then probably you want to have mutex to handle each of them, or semaphores to handle each of them, okay, individually. Okay, so because semaphores do not differentiate between the resources, they treat all resources as the same as long as I use a particular semaphore for a particular group of resources. Okay, so that is an important thing you must understand. Okay, now of course there are issues when we're dealing with semaphores or mutexes. Okay, one of them is what we call a deadlock. Okay, where a situation where multiple tasks hold on to resources that are shared. Okay, and eventually what happens is, because nobody wants to give up, nobody finishes. Okay, now let me give you an example here. So for example, let's say I have process 1, okay, and I have process 2, and I have 2 resources, resource 1 and resource 1 and resource 2. Okay, now let's assume that process 1 is running first, and process 1 at some point of time acquires resource 2. So at this point of time, I got resource 2. Okay, and while it was running, okay, it got after that it got blocked. Okay, and process 2 was able to run. Okay, and process 2, while running, it acquired resource 1. Okay, so it acquired resource 1. Okay, and subsequently what happens, it is still running and it tries to acquire resource 2. Okay, it tries to acquire resource 2, but resource 2 is already acquired by process 1, so it gets blocked. Okay, so since it goes to a block state, what happens, process 1 can resume, and when process 1 resumes, it goes and tries to acquire resource 1, but resource 1 is already acquired by process 2, so again your resource 1 is unavailable, so it get blocked. Okay, so what happens, subsequently process 1 is blocked forever and process 2 is blocked forever, and that's why we say nobody finishes. Okay, so of course this is based on the idea that both resource 1 and resource 2 are required by both process 1 and process 2. Okay, so this is a classic example of a deadlock. So you have 2 processes, process 1 and process 2, and process 1 acquired resource 2 first, but before it could acquire resource 1, what happened was it got preempted, okay, or blocked for some reason, and when process 2 came along, it went to acquire resource 1. Okay, and when it tried to acquire resource 2 at this point of time, it was unable to do it because it was already acquired earlier by process 1. Okay, and since process 2 cannot carry on, it goes to a block state. And when process 1 resumes, it tries to acquire the remaining resource, which is resource 1, and then it realizes it is blocked because process 2 already acquired it. Okay, so this is a scenario to show you how a deadlock can happen, and in this situation, as you can see, both of them will be indefinitely blocked, and there is no way for them to complete. Correct. So there is currently, of course, uh, ideas on how we can go about it, which we will discuss more in the tutorial questions. Okay, but for now, this is the idea of a deadlock. Okay, and the key thing is this: if there's a circular dependency, okay, between tasks, which is what I mentioned just now, where each process has a sequence, also a group of resources, and there is some sequence where one task has acquired some resource but not the other, and similarly for the other task, then this can lead to a deadlock condition. Okay, so we will be discussing more in the tutorials on how we can handle deadlocks and how we can maybe improve our code to prevent such a situation from happening. Okay, so that's about it for this lecture on concurrency. Okay, so in the next lecture, we will be talking about message passing. Okay, in the labs, you will also get a good chance to try out Mutex as well as Semaphores. Okay, and see how we can actually integrate these very important OS functionalities into our mini project as well. Okay, so thank you. I'll see you in class.